This course is on material and heat balance in metallurgical processes. Material and heat balance is regularly and routinely done in a plant to take stock of the input and outputs of the raw material. It is required to perform an analysis of the various sources from where the material is entering and the sources from where material is exiting, in order to keep an account of the loss of material, if at all it occurs during the process. Material balance is also very important, or the first step to perform energy balance. Both material and energy balance, they are required to be done in order to find out the flow of material or the path of flow of the material and energy, in order to identify the loss of material, if at all it occurs, and the loss of energy, if it occurs, and to find the ways to optimize the utilization of raw materials and utilization of energy. Now, material and heat balance has become very important, considering the energy conservation of the processes. Hence, this material and energy balance is routinely done in a plant to identify the methods where the flow of material energy can be optimized. Now, this course aims at the development of problem solving skills, and to see that after going through this particular course, you are able to feel the material and energy requirement of the process. Now, to meet this objective, what I have done, I have collected the problems from various sources, and I tried to present the solved and unsolved problems both. But my appeal to all of you is that you may see the problem, but the solution please see only after when you have attempted yourself. Also, I will see that some concepts of the processes I am going to tell you during the lectures, but the details of the process that I will be omitting, because I am going to stress more upon the material and heat balance and to perform the material and heat balance. So, the basic concepts I will be illustrating, but if you want to know the more details about the process, then I request that you go through the references that I will be giving you time to time and get a feel of that process, because my objective of this particular course is to give a quantitative feel about the material and energy balances in various metallurgical processes, in particular metal extraction and refining. Now, as such, the first lecture that I am going to give you is on the measurement of quantities, units and dimension. I have experienced over the long years of teaching to the students that often there are mistakes in finding out the units, in deriving the units, in knowing the units. So, I have thought, let me introduce to the basic concepts of units and dimensions. Now, as all of you know, all physical quantities need unit in order, for example, to compare the magnitude of the physical quantities from different sources. So, you do require to express the physical quantity in terms of a unit. Now, there are different systems of expressing the unit of the physical quantity. In essentially, there are three methods. There are three methods, or so to call 4 methods, to express the unit of any physical quantities. And these systems, that means the system to express unit of a physical quantity of a physical quantity, say we have system like one is FPS, which all of you know, that is feet, pound and second. Another is CGS, centimeter, gram and second. Still another MKS system, that is meter, kilogram and second system, and last is the SI unit. So, these are the 4 different ways or systems that have been evolved in order to express the magnitude of the quantity. Now, I am giving the table, say for example, if I write here a quantity, then I put here absolute unit, and then first I will put say FPS system, CGS system, MKS system and SI system. Now, here itself I will like to differentiate between the 2 types of units. One is the fundamental unit, that is fundamental unit are those units from where the units of other physical quantities can be derived, and second they are the derived units, that is utilizing the fundamental unit one can derive the units of other physical quantities. So, what I am going to write in this particular table is the fundamental unit in all these 4 systems. So, these fundamental units can be used to derive the units of other physical quantities. For example, and these fundamental units are, say one is the mass. In FPS system it is expressed in pound, and you must have seen in various books it is written as pound. In CGS system it is expressed as gram, and as such short it is written as G. In MKS system mass is expressed in kilograms, and the short form is kg. In SI system also it is expressed as kilogram, this is called kg. Another fundamental unit for the quantity length, in FPS system it is expressed in feet or foot, shortly it is written as FT. Here it is in centimeter, here it is in meter, or you write as meter, and SI units also in meter, right, in meter. Third is the time. In all, whether FPS, CGS, MKS and SI, the time is uniform, that is in the second. It is expressed as second, here it is also second, here it is also second. In SI it is not written SEC, but it is written simply as S. Another is the temperature. Temperature in FPS system it is in degree Fahrenheit, in CGS it is degree Celsius, in MKS it is degree Kelvin, or sometimes it is written as Kelvin, and in SI it is also written in Kelvin. So, and another fundamental unit is also amount of substance, though it has come in mass, but sometimes this is also expressed as amount of substance. In FPS system it is pound mole, in CGS system it is gram mole, in MKS system it is kilogram mole, and in SI units it is simply written as mole. Now, this SI, in fact SI it means, I am just writing separately, SI it means that is system international system, international D units, which means that international system of units, that is international system of units, national system of units. That is what this SI system means. Now, these are the fundamental quantities. Now, there are some derived. Now, these derived quantities are those. So, we have then derived quantities that is utilizing these fundamental units, one can derive the units of other physical quantities. For example, you want to derive the units of area, volume, heat transfer coefficient, mass transfer coefficient and so on. So, by utilizing the fundamental unit, one can derive the unit of, for example, other physical quantities. So, for example, we derive the unit of force. Let us derive the unit of force. Now, force, that is equal to mass into acceleration, mass into acceleration, mass into acceleration. So, in SI unit, that is equal to kg into meter upon second square, and that is equal to 1 Newton, and so you call Newton. So, you know mass kg and acceleration meter upon second square. So, you are getting again kilogram, then meter and second, they are the fundamental units, and utilizing the formula and units of the variable which is in the formula, one can obtain, for example, unit of force. Say in CGS system, that will be equal to gram into centimeter upon second square, and that is equal to called 1 dyne. And also here to note 1 dyne, 1 Newton, that is equal to 10 to the power 5 dynes. So, that is in CGS system. Now, similarly, in MKS system, this is a kilogram, meter and second square. Now, in most cases SI and MKS unit, they are more or less the same, that is equal to 1 Newton. In FPS system, the unit of force, that will be pound, feet upon second square, and that is called 1 poundal. 1 poundal. Similarly, say for example, you want to derive the units of energy. So, let us derive units for energy. So, all that we have to write down the formula. Say energy E, that is equal to half m v square, m is the mass, v is the velocity. So, in SI system, E, that will be equal to kg meter square upon second square, and that is all of you know, that is 1 joule. Similarly, in CGS system, energy will be gram centimeter square upon second square, and that will be equal to 1 erg. That will be equal to 1 erg, and also the interrelation, say 1 joule, that is equal to 10 to the power 7 ergs. That is also to remember. Now, also here to remember that 1 calorie that is equal to 4.184 joule. Sometimes it is book, it is also given 4.183, but you can take 4.184, and this is when you call thermochemical. Now, also 1 calorie in international steam table, that is considered to be equal to 4.1868 joule. There is a slight difference, that is it. Now, similarly, the energy to express in FPS system, we say E, that is pound feet square upon second square, and that is written as feet poundal. Now, here some of the important relationship, say 1 BTU. BTU stands for British thermal units. I write down for you, British thermal unit. So, 1 BTU that is equal to 778 feet pound force, that is equal to 1054.35 joule, and that is also equal to 252 calorie. Now, mind you, these interconversions are many times required, and many times we are confused what value should be used. So, you should be able to derive from the basic quantities. And also to remember, say 1 kilocalorie, it is very simple, 1 kilocalorie that is equal to 1000 calorie. I do not need to write, all of you know, but just to complete my lecture, and that is also equal to 3.968 BTU. Now, I have purposely included the FPS system because many old books, they are still very good. The problems and the various quantities, they are given in the FPS system, many good books. So, that is why I thought to include in my lecture the FPS system also. Now, say let us take third example, derive units for pressure. Derive units for pressure. Again utilizing the fundamental units. So, pressure we define, say pressure, all that you have to define in terms of the formula, that is force upon area. So, now we can obtain the unit. So, that force, if we say kilogram meter upon second square, area is in meter square. So, that becomes Newton per meter square in SI unit. Now, similarly, some relation, say 1 Pascal that is written as PA, that is equal to 1 Newton per meter square, and that is also equal to 10 dynes per centimeter square. Also to know 1 atmosphere, that is equal to 760 torr, that is equal to 1.01325 into 10 to the power 6 dynes per centimeter square, and that is equal to 1.01325 into 10 to the power 5 Newton per meter square, and that is also equal to 14.696 pound force per inch square. Now, also to remember here, say 1 millimeter mercury, 1 millimeter mercury, that is equal to 1 torr, because that is very often used this units in vacuum, and for very low pressure is required, then you express in millimeter mercury. So, that is equal to 0.01934 force per inch square, and that is also equal to 1.333 into 10 to the power 3 dynes per centimeter square. That is also the thing. Also many times 1 bar is also unit. So, 1 bar, that is equal to 10 to the power 6 dynes per centimeter square. Now, dynes per centimeter square is the unit of pressure in CGS system, that is equal to 10 to the power 5 pascals, and that is equal to 0.98692 atmosphere. So, this is about the pressure. Now, sometimes very low pressure is also required to measure, that is in 1 micron, that is mu, that is equal to 10 to the power minus 6 meter mercury, that is equal to 10 to the power minus 3 millimeter mercury, that is equal to 0.1333 Pascal. Many times you require to express the unit of power. So, let us take it now, express the unit of power, because these things we will very often require while formulating the problems of material and heat balance in metallurgical processes. So, power, let us say 1 watt, that is equal to 1 kilogram meter square upon second cube, and that is equal to 1 joule per second, 1 joule per second. Also it is expressed many times 1 horsepower, 1 horsepower, that is equal to 550 feet F per second, that is equal to 746 watt. Many times we require to express what should be the horsepower of the pump or horsepower of the motor in order to transport a particular amount of water from one place to another, and that is why you also require the unit of horsepower. Now, the 1 kilowatt, that is all of us we know, simply I am putting it, that is equal to 1000 watt, that is equal to 3414 BTU per hour. Also many times it is also required to express the power consumption in kilowatt hour. So, 1 kilowatt hour, that is I am writing approximately, that is equal to 860 kilocalorie, and that is equal to 3414 BTU. So, this is about the some of the say deriving of the units from the basic unit. Similarly, you can derive the unit of any physical quantity by utilizing the fundamental unit. The fundamental unit are mass, length, temperature and time. These are the fundamental units. On mass you can express in kilogram or kg mole, whichever way you want to express it. Now, similarly, the specific heat, well I will not be deriving in all dimensions, but the specific heat from the definition you write as joule per kg Kelvin, that is amount of heat required to raise the temperature of 1 kilogram by 1 degree, and that is expressed for example in joule, kg and into Kelvin. Similarly, other systems CGS and FPS and MKS, one can derive the units. Now, here some of the prefixes are important. Some of the prefixes, sometimes there occurs a confusion, I thought let me give you. So, prefixes, you write tera is written as T and its value is 10 to the power 12. Giga is say G and its value is 10 to the power 9. Mega is M, this is 10 to the power 6. Kilo, well all of you know kilo, I do not need to say. K, it is 10 to the power 3. Then deci, it is as D, 10 to the power minus 1. Milli, M, which is 10 to the power minus 3. Micro, mu, 10 to the power minus 6. Then nano, which is now very important, N, the value is 10 to the power minus 9. That is how the various are there. Temperature can be expressed in degree Fahrenheit or degree Kelvin or degree Celsius. Degree Rankine is also one of the unit, and the interrelationship I hope you must be knowing, it is from the very basic. Now, another thing that is often expressed is gram mole, say gram mole, kilogram mole, then pound mole, or many times we write gram atoms. And to find out the value of gram mole, for example, you divide the mass by its molecular weight, you get the gram mole. Kilogram mole, gram mole, only the difference of 10 to the power 3, and pound mole, again you divide the mass in pound, divide by its molecular weight. So, these are also the ways of expression of the content of the mass. Now, it is also necessary to define here the molar volume. Molar volume. Now, this molar volume is defined either on the basis of 1 gram mole, defined either on the basis of say 1 gram mole or 1 pound mole. And while specifying the volume, one has to specify the temperature and pressure both. Expression of volume in meter cube, it requires to specify what is the temperature and what is the pressure at which that volume is expressed. So, 1 gram mole of an ideal gas, 1 gram mole of an ideal gas it rather occupies 22.415 liter, or we can approximate it to say 22.4 for calculation, and this to remember this is at 0 degree C and 760 millimeter mercury. This point is very important to note. Now, similarly, if you want to express now say at 25 degree Celsius, say 1 gram mole of an ideal gas, say 1 gram mole of an ideal gas, that is equal to 24.467 liters. Now, here this is at 25 degrees Celsius and rather 1 atmospheric pressure or 760 millimeter, whichever way you want to express. Now, remember, so accordingly you have the, to express the volume, you have to express the temperature and pressure simultaneously. Now, similarly, another variable which is often, that is specific volume. Specific volume. Specific volume is reciprocal of density. Reciprocal of density, and that is equal to either centimeter cube per gram or meter cube. Here it will be now per kg or feet cube per pound. These are the ways of expressing specific volume. Now, composition. Composition can be expressed in terms of mole fraction or mass fractions. Say mole fraction or mass fraction. It is very simple. If you have the different elements in a mixture, then you find out the moles of each element, find out the total moles and divide. If you divide by the if you divide the moles of an element by the total moles, then you get the mole fraction. Similarly, mass, add the total and divide it and you get the mass fraction. Now, another very important thing that you have to know is also the value of universal gas constant. So, I will try to derive, because very often these value of R is needed in dealing with the gases. So, value of R, you know, very simple, that P 1 upon V 1, P 1 into V 1 upon T 1, that is equal to P 2 upon P 2 into V 2 upon T 2, and that is equal to R. So, we can find out now R, for example, that is equal to P 0 into V 0 upon T 0. So, if we express, say, P 0 is atmospheric pressure and V 0 if we express at 22,415, we divide by 273. So, that will be coming, the unit will become equal to 82.10 centimeter cube atmosphere. Since I taken 1 gram mole of the gas, 1 gram mole into degree Kelvin. So, this 22,415 centimeter cube atmosphere 1 per gram mole upon degree Kelvin. Now, in CGS units, for example, if you want to express R, in CGS unit, if you want to express, then we have to express P 0, and P 0 that is equal to 1.01325 into 10 to the power 6 dynes per centimeter square. T 0 273 degree Kelvin and V 0 that is equal to 22415 centimeter cube per gram mole. So, all that now I have to substitute, and if I substitute and solve, I will be getting the value of R, that will be equal to 1.988 calorie per gram mole degree Kelvin. All that these values you have to substitute, say P 0, T 0, V 0 into R is equal to P 0 V 0 upon T, and you get R in case of CGS units 1.988 calorie per gram mole per degree Kelvin. So, the value of R, let us derive in SI unit. In SI unit, again say here P 0 that is equal to 1.01325 into 10 to the power 5 pascals, T 0 273 Kelvin, and V 0 that is equal to 0.022415 meter cube per gram mole. So, I am substituting now the value, say R that is equal to 1.01325 into 10 to the power 5 into 0.022415 divide by 273, and I will try to derive the units, that is equal to in Newton per meter square, unit of P, then I substituted V in meter cube per gram mole, that is what I have done, and then I divide by 1 upon degree Kelvin. So, if I solve this side of the unit, then it comes Newton meter upon gram mole degree Kelvin, and Newton meter we know that is kilogram meter into meter upon second square gram mole degree Kelvin, and this you know kilogram meter square upon second square, this is joule. So, the unit has become joule upon gram mole degree Kelvin, and if I solve here, that will be equal to 8.314 joule per gram mole degree Kelvin. So, you are seeing this value of R we are able to derive in by utilizing the fundamental units kilogram, meter, second and degree Kelvin. So, that illustrates that in order to derive the units of any physical quantity, if one uses the fundamental units, which is mass, length, temperature and time, one can in fact derive the units of almost all physical quantities as I have illustrated over here. Similarly, if I want to derive in MKS system, if I want to derive, and this I will leave on you to derive these units and get this R that is equal to 8314 joule upon kg mole into degree Kelvin. So, you try to derive these units in terms of MKS system, also try to derive in terms of CGS system and so on. Now, this is about the units. Now, also the many metallurgical processes have feed or product streams that contains moisture, that is this feed is a mixture of solid and liquids. So, these mixtures of solid and liquid, say mixture of solid plus liquid, in metallurgical terminology this is called a slurry. It is called slurry. A slurry consists of solid and liquid mostly it is water is used. So, the concentration I mean for transportation purposes of a slurry, it is important to know what is the concentration of solid in a slurry. because you may be using a pump to transport the slurry from one location to another location, and this term slurry will come very often in my lecture on material and heat balances. So, please be clear. So, concentration of solids in slurry, concentration of solids in slurry that can be expressed either as wet percent solid or volume percent solid, whichever way we want to express. Now, it is also very often required to know what is the wet percent solid in a slurry, because many times you can't measure these wet percent solid in a slurry, it is difficult to measure. So, you may be measuring some indirect measurement, say by measuring the density and so on, one can determine the weight percent of the solid in a slurry, and you can convert that weight percent into the volume percent of the slurry. So, let us derive the relationship, say relationship between weight percent solid let us call it is percent x, specific gravity of solid phase, specific gravity of solid phase, let us put rho s, and that of slurry put equal to rho m, and we use water as a medium of slurry, water as a medium of making slurry. So, we can derive the relationship very simple, say for example, say volume of slurry that is equal to volume of solid plus volume of water. So, if we take 1 kg slurry, which has solid as percent x, then we can write down this, say 1 upon rho m, that is equal to percent x upon 100 rho s plus 100 minus percent x, that is the amount of water, divide by 100 into W, where 100 into W. So, from here we can derive the percent x, or that is in weight percent, that will be equal to 100 rho s rho m minus 1000, because I am using the density of water is 1000 kilogram per meter cube, that divide by rho m into rho s minus 1000. So, utilizing this expression, one can determine the percent solid simply if you know the density of the slurry and density of the solid. Of course, density of water is known, which is taken here 1000 kilogram per meter cube. So, now say volume percent of slurry, volume percent of slurry, volume percent of solid in slurry, that will be equal to wet percent into density ratio. So, that is how one can determine these wet percent or volume percent of solid in a slurry. Now, just let me illustrate. So, if I illustrate it, let us calculate a specific gravity of slurry, calculate a specific gravity of slurry which contains 65 wet percent lime. The specific gravity of lime, the specific gravity of lime is given to you 2600 kilogram per meter cube. Take density of water as it is in the formula, density of water take equal to 1000 kilogram per meter cube. Now, I mean when I say slurry, that is always, I mean most of the cases it is made in water. So, it is very straightforward, all that we have to use the formula. So, I just put it here, the formula is there. So, 65 that is equal to 100 into 2600 rho m minus 1000 upon rho m 2600 minus. So, all that we have to find out the value of rho m. So, I am leaving the exercise on you, you can do it. So, value of rho m that will come out to be equal to 1.667 into 10 to the power 3 kilogram per meter cube, or you can also put it 1667 kilogram per meter cube. Now, if I want to say volume percent of slurry, I want to determine volume percent of solid in slurry, that will be equal to 65 into 1667 upon 2600, that will be equal to 41.66%. That is how you can find out the wet percent of solid in a slurry or volume percent of solid in slurry. Now, if you want to also find out, let us find out, say, now it is also important to find out mass flow rate, is also to find out, say, mass flow rate of dry solid in slurry, dry solid in slurry. Now, these things are very important when we enter into the material balance of metal extraction and refining. A large amount of slurry is to be handled and one needs to know what is the mass flow rate. So, this mass flow rate you can find out by, say, volumetric flow rate, if it is given, volumetric flow rate into slurry density, into percent x, the wet percent solid, and you divide this thing by 100. So, if I take it in terms of formula m, that is equal to F, which is the volumetric flow rate, rho m is the density of slurry to percent x upon 100, that is equal to in kilogram per hour, where F is in meter cube per hour. Now, if I use, that is, if I replace this percentage x from the earlier formula, then I get mass flow rate that will be equal to F rho s rho m minus 1000 divided by rho s minus 1000. So, you can also determine the mass flow rate by utilizing this particular formula. Let me explain to you by solving a particular problem. So, now calculate how many kg of magnetite must be added to 100 kg water to make up a slurry with a specific gravity say rho m, that is 1.4 gram per centimeter cube. The specific gravity of magnetite is given, specific gravity, that is rho s of magnetite is given, and this value is given to you 5.2 gram per centimeter cube. So, we have to calculate this. You have the formula. So, I will try to apply for you, so that you understand. Now, weight percent solid, we can straightaway find out weight percent solid, that will be equal to 100 into 5.2 into 1.4 minus 1 upon 1.4 into 5.2 minus 1. So, that will be equal to 35.4%. Now, say weight percent of water, that is equal to 64.6%. Now, I know that total mass upon mass of water that is, if I put it m upon mH2O, that is equal to 100% upon 64.6%. So, from here I can find out that is equal to 100 upon 64.6 into 100. So, that becomes 155 kg. This is the mass of the total mixture. So, from here mass of magnetite that will be equal to 155 minus 100, that will be equal to 55 kg. That is the answer. That means, I have to add 55 kg of magnetite in order to make a slurry of density 1.4 gram per centimeter cube, and this particular thing is often required for various mineral processing operations.